Every year, companies like Apple, NVIDIA, AMD, Intel, and Qualcomm invest billions of dollars designing faster and more powerful chips. Those designs are then manufactured by companies like TSMC and Samsung, fueling an industry worth hundreds of billions of dollars and powering everything from smartphones to artificial intelligence. At first glance, it looks like a fiercely competitive industry, where every company is racing to build the next technological breakthrough. But beneath that competition lies a dependency shared by every leading chip maker. No matter who designs the chip, no matter who manufactures it, at the most advanced level, they all rely on the same company. ASML. What's remarkable is that ASML doesn't design processors. It doesn't manufacture chips. And it doesn't sell consumer electronics. Yet some of the world's most valuable technology companies depend on its products to build their most advanced semiconductors. Which raises an important question. If ASML doesn't compete with Apple, NVIDIA, Intel, or TSMC, how does it control the global chip industry? The answer isn't ownership. It isn't market share. And it certainly isn't because ASML makes the chips itself. Instead, ASML controls something far more fundamental, a technological bottleneck that every advanced semiconductor must pass through before it can ever be manufactured. And once you understand that bottleneck, you'll understand why one company from the Netherlands has become one of the most strategically important businesses in the modern world. ASML's influence doesn't come from designing better chips. It comes from controlling the most critical step in making them. In the semiconductor industry, every company competes to design faster processors. But no matter how innovative a design may be, it has no value unless it can be manufactured reliably and at scale. That's where the industry's biggest bottleneck begins. Manufacturing an advanced semiconductor isn't simply a matter of producing silicon. It's the challenge of building billions of microscopic transistors with extraordinary precision, layer after layer, across an entire wafer. As chips become more powerful, those transistors become smaller. And the smaller they become, the harder they are to manufacture. Eventually, every leading chip maker reaches the same technological barrier. And overcoming that barrier is exactly where ASML built its dominance. If manufacturing is the semiconductor industry's biggest bottleneck, then what created that bottleneck in the first place? The answer is the industry's relentless pursuit of smaller transistors. For decades, shrinking transistors has been the foundation of technological progress. Smaller transistors allow more computing power to fit into the same chip, making devices faster, more energy efficient, and more capable. But every reduction in size also makes manufacturing dramatically more difficult. At just a few nanometers, engineers are no longer working with features visible under a conventional microscope. They're manufacturing structures only a few dozen silicon atoms wide. At that scale, precision is no longer an advantage, it's a requirement. And that's exactly where the balance of power in the semiconductor industry begins to change. Because once manufacturing reaches these physical limits, success is no longer determined by who designs the best chip. It's determined by who possesses the technology capable of manufacturing it. So what technology made manufacturing at this scale possible? Manufacturing an advanced chip involves hundreds of highly specialized processes. But among all of them, one step determines just how small and powerful a chip can become. That step is called photolithography. At its core, photolithography is the process of transferring incredibly complex circuit patterns onto a silicon wafer. Every transistor, every connection, every microscopic feature that defines a modern processor begins as a pattern created during this stage. As chips continue to shrink, creating those patterns becomes the single greatest technical challenge in semiconductor manufacturing. And that's precisely where ASML established its strategic advantage. But if photolithography has existed for decades, why did it suddenly become so difficult? For decades, photolithography continued to improve, allowing the semiconductor industry to manufacture increasingly smaller transistors. But eventually, engineers encountered a problem that couldn't be solved simply by building better machines. It was a problem rooted in the laws of physics. Photolithography works by projecting light through a circuit pattern onto a silicon wafer. Just like a camera cannot capture details smaller than the wavelength of visible light, lithography also faces a fundamental limit. The smaller the transistor, the shorter the wavelength of light required to print it accurately. As the industry pushed toward chips measured in just a few nanometers, the existing generation of lithography machines was approaching its physical limits. This wasn't just another engineering challenge. It threatened to slow the entire pace of semiconductor innovation. And solving that problem would require an entirely new generation of technology. That technology would become one of the most ambitious engineering projects ever attempted. The semiconductor industry didn't need a better lithography machine. It needed an entirely different way of making chips. That breakthrough came in the form of extreme ultraviolet lithography, or simply EUV. Instead of relying on the same wavelength of light that had powered chip manufacturing for decades, EUV uses light with a wavelength nearly 15 times shorter. That single change allowed manufacturers to print far smaller and more complex transistor patterns than ever before. More importantly, it extended the industry's ability to keep shrinking transistors without sacrificing precision. In other words, EUV didn't just improve semiconductor manufacturing. It preserved the industry's roadmap for building faster, more powerful chips. And while many companies recognized the importance of EUV, only one succeeded in turning it into a commercially viable machine. That company was ASML. But building an EUV machine turned out to be one of the most difficult engineering challenges in modern history. Building an EUV machine wasn't a matter of improving existing lithography technology. It required engineers to rethink almost every critical system from the ground up. The light source, the optics, the motion systems, the vacuum environment. Each presented a challenge that had never been solved at an industrial scale. But solving these challenges individually wasn't enough. Every subsystem had to operate together with extraordinary precision, because even the smallest deviation could affect the manufacturing of billions of microscopic transistors. The result wasn't just another piece of semiconductor equipment. It became one of the most sophisticated machines ever engineered, combining breakthroughs in physics, optics, materials science, precision engineering, and software into a single manufacturing platform. And the more complex the machine became, the more difficult it became for anyone else to build one. But engineering complexity alone doesn't explain ASML's dominance. The real advantage was that every technological breakthrough became another barrier for competitors trying to catch up. The extraordinary complexity of EUV machines had an important consequence. It left the semiconductor industry with only one company capable of producing them at scale. For leading chip manufacturers, the challenge was no longer finding the best lithography technology. There simply wasn't another commercially viable alternative. As advanced chips became increasingly dependent on EUV, every major manufacturer arrived at the same destination. Whether it was TSMC, Samsung, or Intel, they all had to rely on ASML to move to the next generation of semiconductor manufacturing. That fundamentally changed ASML's role in the industry. It was no longer just another equipment supplier. It became the only gateway to the world's most advanced chip manufacturing. And when an entire industry depends on a single gateway, influence naturally follows. But being the only supplier didn't automatically give ASML control. That influence grew because chipmakers began building their long-term strategies around ASML's technology. Being the only supplier of EUV machines gave ASML something far more valuable than market share. It gave the company the ability to influence the pace of innovation across the semiconductor industry. Developing a new generation of chips is a process that begins years before a single chip is ever manufactured. Chipmakers must commit billions of dollars to new fabrication plants, manufacturing processes, and production technologies long before they reach commercial production. Those decisions depend on one critical question: when will the next generation of manufacturing technology be ready? For the world's leading semiconductor companies, that answer increasingly came from ASML. As each new generation of EUV systems became available, chipmakers aligned their development plans with ASML's technology timeline. ASML didn't decide which chips companies would design. But by determining when the necessary manufacturing technology became available, it increasingly influenced when those chips could be manufactured. In the semiconductor industry, where being first can determine billions of dollars in revenue and market leadership, controlling the pace of manufacturing innovation is a form of strategic influence. And that's how ASML's technological leadership evolved into industry-wide control. But once an entire industry builds its future around a single technology platform, changing course becomes extraordinarily difficult. Once a chipmaker commits to a manufacturing platform, changing course is no longer a simple purchasing decision. It's a decision that can reshape years of engineering, billions of dollars in investment, and the timeline of future products. Every advanced semiconductor process is carefully optimized around specific manufacturing equipment. Engineers spend years refining production techniques, improving yields, and integrating each generation of lithography into an increasingly complex manufacturing system. Replacing that foundation isn't as simple as installing a different machine. It means revalidating manufacturing processes, retraining engineering teams, and accepting years of uncertainty before production can return to full scale. For companies competing in markets where every product cycle matters, those delays can be just as costly as the financial investment itself. That's why the decision to adopt ASML isn't merely the purchase of a machine. It's a long-term commitment to an entire manufacturing platform. And the longer that platform remains at the center of semiconductor production, the stronger ASML's influence over the industry's future becomes. But even switching costs don't fully explain why ASML remains so difficult to challenge. The company's strongest advantage lies in an ecosystem that no competitor has been able to recreate. Technology alone doesn't explain why ASML has remained years ahead of every potential competitor. Its greatest advantage is the ecosystem that has grown around it over decades. Every EUV system depends on hundreds of highly specialized components, many of which are produced by companies that are global leaders in their respective fields. But these suppliers aren't simply vendors delivering parts. They have spent years co-developing technologies alongside ASML, solving engineering challenges that no company could overcome alone. That collaboration created something far more valuable than a supply chain. It created a network of expertise, manufacturing knowledge, and technological experience that became deeply integrated into every generation of ASML's machines. For a competitor, replicating an EUV system wouldn't just mean designing a similar machine. It would mean rebuilding decades of trusted partnerships, shared innovation, and accumulated know-how across an entire industrial ecosystem. And that's why ASML's competitive advantage extends far beyond the technology inside a single machine. It's embedded in an ecosystem that the semiconductor industry itself helped build, and continues to depend on. By this point, ASML had become far more than a successful technology company. It had become a strategic asset, not only for the semiconductor industry, but for governments around the world. By this point, ASML was no longer just a supplier to the semiconductor industry. It had become a company whose technology influenced the future of computing, artificial intelligence, telecommunications, and national defense. In the past, governments were primarily concerned with securing natural resources such as oil, gas, and rare minerals. Today, advanced semiconductors have become just as strategically important. They power everything from military systems and critical infrastructure to cloud computing and AI. And without the ability to manufacture the most advanced chips, technological leadership becomes increasingly difficult to maintain. That reality transformed ASML from a successful Dutch technology company into a strategic asset with global significance. Decisions involving ASML were no longer viewed solely as commercial transactions. They became matters of economic security, technological leadership, and national strategy. That's why governments around the world began paying close attention to a company that, until recently, few people outside the semiconductor industry had even heard of. Nowhere has that strategic importance become more visible than in the growing technology rivalry between the United States and China. ASML's strategic importance became impossible to ignore as tensions between the United States and China intensified. Both countries recognize that advanced semiconductors are no longer just commercial products. They are essential to artificial intelligence, advanced manufacturing, military technology, and long-term economic competitiveness. But designing advanced chips is only part of the equation. Manufacturing them requires access to the world's most advanced lithography systems. And for those technologies, there is effectively only one supplier. That placed ASML at the center of one of the most significant technology rivalries of the 21st century. The company didn't choose that position. It earned it by becoming the only provider of technology capable of manufacturing the world's most advanced semiconductors. As a result, decisions involving ASML increasingly carried consequences that extended far beyond the semiconductor industry. They became decisions with global economic and geopolitical implications. That is why access to ASML's most advanced machines is no longer determined by market demand alone. For most technology companies, success is measured by how many customers they can reach. ASML operates under a very different reality. For its most advanced machines, access is determined not only by commercial agreements, but also by government approval. Over the past several years, export restrictions have limited the sale of ASML's most advanced EUV systems to certain markets. The objective isn't to restrict ASML itself. It's to limit access to the manufacturing technology required to produce the world's most advanced semiconductors. That distinction is critical. Governments aren't controlling who can design advanced chips. They're controlling who can manufacture them. And because ASML sits at the center of that manufacturing capability, its technology has become one of the most strategically regulated assets in the global semiconductor industry. It's a powerful reminder that in today's world, the most valuable technologies aren't always the products consumers recognize. Sometimes, they're the tools that make every other breakthrough possible. But export controls raise an even bigger question. If access to ASML's technology can be restricted, why hasn't China simply developed its own alternative? At first glance, the solution seems straightforward. If access to ASML's most advanced machines is restricted, why not build an alternative? In reality, that's far easier to propose than to accomplish. Developing an EUV system isn't a matter of investing more money or hiring more engineers. It requires decades of accumulated knowledge across physics, optics, precision manufacturing, software, and industrial engineering. More importantly, it requires an ecosystem where hundreds of specialized companies can innovate together, refine technologies over many years, and reliably manufacture components at an extraordinary level of precision. That's not something that can be replicated through a single national program or accelerated by financial investment alone. It's the result of decades of continuous collaboration, engineering experience, and industrial learning. Which is why catching up to ASML isn't measured in months or even years. It's measured in technological generations. And that raises one final question. Can ASML maintain this extraordinary position forever? Throughout this video, we've examined how ASML built one of the strongest competitive positions in the global semiconductor industry. The company controls a critical manufacturing bottleneck, operates without a meaningful direct competitor, and has built an ecosystem that has taken decades to develop. For engineers, those achievements represent extraordinary technological success. For investors, they represent something different. They represent the characteristics of a business capable of generating durable cash flows over a very long period of time. Markets rarely assign premium valuations simply because a company builds remarkable products. They assign premiums to businesses that can protect their competitive advantages, maintain pricing power, and continue creating value even as industries evolve. That's what makes ASML different. Its valuation isn't built on the expectation of one successful product cycle. It's built on the expectation that the company's competitive position can endure for many years to come. But a premium valuation isn't supported by reputation alone. It has to be backed by the economics of the business itself. Premium valuations aren't sustained by great stories. They're sustained by exceptional business economics. ASML possesses several characteristics that investors consistently value. First, the company has extraordinary pricing power. Its customers don't choose ASML because it's the cheapest option. They choose it because, for the world's most advanced chips, there is no comparable alternative. Second, every machine ASML installs creates a long-term relationship. Customers continue relying on the company for maintenance, software upgrades, and productivity improvements throughout the life of the system, making each sale the beginning of years of recurring revenue rather than a one-time transaction. Third, demand for ASML's most advanced systems is driven by long-term technology roadmaps, not short-term consumer trends. That gives the business a level of visibility that few capital equipment companies can achieve. Combined with high barriers to entry and decades of accumulated expertise, these characteristics create a business capable of generating strong returns while remaining remarkably difficult to disrupt. That's the foundation behind ASML's premium valuation, not optimism, but business quality. Of course, no competitive advantage is permanent. The real question is what could eventually weaken a business this strong. Every investment thesis should be tested by one simple question. What could change the story? ASML's competitive position is exceptionally strong, but it isn't immune to risk. The first is execution. The semiconductor industry is counting on ASML to deliver increasingly complex technologies, including the next generation of high-end EUV systems. Delays, manufacturing challenges, or slower-than-expected adoption could postpone the industry's technology roadmap. The second is cyclicality. Semiconductor demand has always moved in cycles, and periods of reduced capital spending can temporarily slow customer investment, even when ASML's long-term competitive position remains intact. And finally, geopolitics. as ASML's technology becomes increasingly strategic. Throughout this video, we've explored how ASML built one of the strongest competitive positions in the global technology industry. A company that controls a critical manufacturing bottleneck, operates without a meaningful direct competitor, and continues to shape the pace of semiconductor innovation. Businesses with these characteristics rarely trade at ordinary valuations. Investors are often willing to pay a premium because they believe those competitive advantages can generate exceptional cash flows for many years into the future. Using a range of valuation scenarios, our historical fair value estimate for ASML is approximately $1,070 per share, with a more conservative estimate near $609 and an optimistic scenario approaching $1,980. These figures shouldn't be viewed as precise price targets. Instead, they represent a framework for thinking about how different assumptions about growth, profitability, and competitive durability can influence intrinsic value. Ultimately, the most important takeaway isn't whether ASML trades slightly above or below any single valuation estimate. It's whether the company can continue protecting the extraordinary competitive advantages that we've examined throughout this analysis. Because over the long run, business quality is what drives intrinsic value, and intrinsic value is what ultimately drives shareholder returns. Throughout this analysis, we've asked one fundamental question. How does ASML control the global chip industry? The answer was never about owning the largest market share or selling the most machines. ASML built its position by controlling the industry's most critical manufacturing bottleneck, a position strengthened over decades through technological leadership, relentless innovation, and an ecosystem that remains extraordinarily difficult to replicate. That's more than a technological achievement. It's the foundation of an exceptional business. For investors, that's the lesson that matters. Markets don't reward companies simply because they build remarkable products. They reward businesses capable of protecting their competitive advantages, generating durable cash flows, and creating value over decades. That's why companies like ASML rarely appear cheap. Their premium valuation isn't driven by hype. It's driven by the market's belief that their competitive advantages can continue compounding far into the future. Of course, no investment thesis is permanent. The question isn't whether ASML is an extraordinary business. The real question is whether it can remain extraordinary for longer than the market already expects. Because in investing, the greatest opportunities don't come from finding good companies. They come from recognizing exceptional businesses before the full power of their long-term economics is completely reflected in price. As always, this video is not financial advice. Please do your own research before making any investment decisions. Thank you for watching, and if you enjoyed this analysis, don't forget to like, subscribe, and share your thoughts in the comments below.